Good morning. All right. Well, thank you. It's a great pleasure to be here. Thanks for joining us this morning. I want to talk about something that I'm passionate about, and I'm sure a lot of us here are passionate about, is about programming languages and paradigms. A real show of hands. How many of you are programmers here? All right, I'm in the right place. That's great. Just wanted to make sure. So let's talk about programming languages. What programming languages do you use? Throw some names at me. Java. Okay, let's start with Java for a minute. What else? What was that? Kotlin. Okay. Groovy. Let's see, we can put that right about here. What else? JavaScript. There's always one of them. Okay. What else? Scala? All right, let's put that right about here. Well, I love C++. I'll put that in there. Maybe a few other languages. Well, we'll see why I put these in these places. We'll come back to that a little later. So we talked about a few different languages. You said you're all programmers, but let me start with the question. Who are we? And if you ask a group of people who we are, you're going to get answers something like this. You're going to have people say they are programmers, they are coders, they are developers, they are data scientists, they are computer scientists, they are software engineers, they're managers, they're architects. But who are we really? I'm going to say we're not any of those. What we really are is we are problem solvers. That's what we really are fundamentally. I know what you're thinking. Some of us create more problems than we solve. But nevertheless, we are problem solvers. That's what we are. And in the grand scheme of things, what do we go to work every single day? We go to work to solve problems. That's what we do. And as part of solving the problem, a small part of that really is the programming languages that we use. And don't get me wrong, I love programming languages. I spend a lot of time learning and thinking about programming languages. Today, I program in about 15 different programming languages. What I'm telling you in so many words is I'm not good in any one of them. But I love learning about programming languages. I like to think about programming languages. And nevertheless, programming languages are a small part of that big puzzle solving the problems every single day. And so languages play a very important role in that, but a very small role nevertheless. But what is a language? Well, just like we have human, natural languages, we have programming languages for almost the same purpose. It is really to communicate. And so languages really are communication tools. And I view programming languages like communication tools as vehicles. Like, for example, on a given day, you probably use a bicycle or use a car, or like I did this morning, I arrived in an airplane, and then I took a taxi to get to my hotel. And so on a given day, you may be using multiple vehicles. Similarly, on a given day, you might want to use multiple programming languages, because languages are really tools or vehicles to get us around different terrains, if you will. So it's a great communication tool. And when it comes to it, one of the things I care about a lot about programming languages is the expressive nature of programming languages. Languages are a form of expression. When I started programming about 30 years ago or 35 years ago, I started programming because I was intrigued by the math and the science and the engineering in programming. And a good 30 plus years later, I'm still programming, honestly, not as much because of the science and engineering and math in it, but more so because of the art in programming. In a way, if you really think about it, programming to me is like writing a poem. You could go to somebody and say, write me a poem about love, or write me a poem about nature, or whatever that you want to ask. The number of poems that could be written about a topic is almost infinite. Similarly, the number of code you could be writing to solve a problem is almost infinite. Not only can you have different variations of algorithms, but you can also have different variations of implementations of the same algorithms as well. And to me, that is beautiful because I have this luxury of writing code and then rewriting the code and refactoring it and then trying to make it elegant. And then when I think I am done, I will go show it to a colleague and have them tell me to rewrite it all the way again. And that's a form of expression that I'm absolutely delighted about when it comes to programming languages and programming in general. Well, in that regard, I want to think about programming languages in general. Now, the good news is almost every single programming language that we use today is Turing complete. But unfortunately, though, while it's great to know it's Turing complete, that gives us a basis for whether a language can be used as a general purpose language, that's awesome. But I would argue Turing completeness is simply necessary but not sufficient in selecting a language. Because in my opinion, telling a language is Turing complete is like saying that most humans can sing. Trust me, you don't want me to be singing up on the stage today. That would be a really horrible experience for you, more than me, I think. But the point really is that just because languages are Turing complete doesn't say a lot of things, unanswered questions. For example, is the language efficient? Is it easy to use? Is it really good in performance? Is it efficient? Is it usable? Is it maintainable? And a lot of these questions are never answered by Turing completeness. But when it comes to adopting a programming language, these concerns are extremely important, some more so than others, depending on various other issues. One of the things to also think about is testability. Sometimes libraries and frameworks and tools and languages tend to be more testable versus less testable. I mentioned earlier that I program in about 15 different languages. So often one of the things that people ask me is, what is your preferred language? I never answer that question. But a couple of years ago, I started a new project. And I went through the notion of selecting a language. And I had this luxury of selecting from 15 different languages because I knew these 15 different languages. And I did. And a few months later, I was sitting with the language author. We were talking about in a conference. And I was mentioning about this particular application I had started building. And this language author asked me what language I chose for my particular application. And I said the language I chose, and the particular author was disappointed and said, how come you didn't choose my language? And the answer to that question is, well, I really focused on testability in this particular scenario. And with all respect, I love your language and tool. But this was a better testability in this other language and platform. So I care a lot about testability as well. And how easy can I really implement my automated test makes a big difference in selecting the language, among a lot of other things I mentioned over here. So in that regard, languages come in different flavors. Now think about flavors of languages for a minute. We listed a few languages earlier, things that you mentioned. But let's talk about languages. But in general, people talk about languages. They talk about static typing, and they talk about dynamic typing. But it's really important to realize that there's more to this than static typing and dynamic typing alone. So I put static typing on the top, and I put dynamic typing on the bottom. But I'm going to put strong typing on the left side, and I'm going to put weak typing on the right side. Now, what is the difference between all these four things? Well, static typing, as we know, is the type information is verified at code writing time or compile time. On the other hand, dynamic typing is where the type information is not really communicated at code writing time or compile time. Well, on the other hand, there is also a sense to what's happening at runtime. When you run the code, is there a verification of type sanity? And if that happens, I would say that is strong typing. But on the other hand, when the code is executed, it doesn't really care about or enforce the type information. I would argue that is actually a weak typing. Now, when you look at it then, the languages are just not statically typed or dynamically typed. We could start placing languages on these four quadrants, if you will. Take the example of Java. We all know that Java is statically typed. But what happens when you run your Java code on the JVM? Well, the JIT compiler is going to verify type sanity at runtime. Not too often, thankfully, but occasionally we do get a class cast exception in Java. And the reason we get a class cast exception in Java is at runtime it verifies the type sanity for us as well. So from that point of view, Java is statically typed, but Java is strongly typed as well. On the other hand, think about languages like C++. Does anyone program in C++ here? It's okay, you're among friends. You can raise your hand. I can see people slowly raising the hand. That's okay, we're among friends. I programmed in C++ for about 15 years. And honestly, I won't hesitate to admit this. I love C++. Because C++ is a language that here's my understanding of C++. This is the timeline. This is your age or timeline. This is when you don't know C++. And then you start learning it. And one day you will say, I know C++. And then a few months later, you're like, I don't know C++, right? And that's when you really understand that you don't understand this language. It's pretty complex. But what about C++? C++ is a statically typed language. We know this. But what happens once you compile your C++ code? Well, once you get that binary, all bets are off. What's going to happen? Well, whatever is going to happen is going to happen. It is just like that in C++. It depends on what's on the V table. It just run over and do stuff. If you don't believe me, ask any of those C++ programmers. Or even better, if you know a C++ programmer, just watch them in the morning. They are so eager to go to work because they have no clue what the code is going to do when they go to work. And this is one of the evidences of C++ being a static type language, but it's also a weakly type language. On the other hand, languages like Groovy and Python and Ruby and Clojure, a lot of these languages, of course, as we know, are dynamically typed languages. But when you look at these languages like Ruby and Groovy and Python, they are dynamically typed. However, when you run the code, you still get validation on the type. So as a result, you'll get a runtime error if you mess up with types, and it'll safeguard you to a certain extent. So these languages, of course, are dynamically typed, but they're also strongly typed. But of course, no talk on programming languages will ever be complete if somebody doesn't mention the best language humans have ever created. You know what I'm talking about? JavaScript. Now, JavaScript is special. And we all know this. We know that JavaScript is dynamically typed. But what happens when you run JavaScript? It's called a miracle. It does whatever it wants to do. And it's going to run over and behave. That's what it runs. You never say, my code works. You always say, my code behaves, because you cannot define it properly. And so when we run JavaScript, it is dynamically typed, but it is also weakly typed. I don't know who said this on Twitter the other day, but this was a brilliant statement, I think. This person said, JavaScript is weakly typed because every week I wonder what the code is doing. So that's a way to think about this is a language that is dynamically typed. It's also weakly typed language as well. Now, of course, you have listed a few languages here for me. So there's a reason I placed these languages in these different places. And let's go ahead and try to see what these languages, how they pan out to be. And you can see the languages you mentioned kind of fit into that readily right there. So we can see how the languages like Java, Kotlin, and Scala are statically typed, but they're also strongly typed. And of course, C++ is a static and the weakly typed language. On the other hand, Groovy, there's a reason I placed it over there, is it's a strongly typed and dynamic type. And of course, you know that Groovy supports static typing as well. So you could say that Groovy kind of moves between those two, maybe somewhere closer to the line than below. And then, of course, JavaScript is weakly typed. So we can see that languages kind of pan this as time goes on. You can see how these languages evolve and provide some of these capabilities in terms of these languages. But of course, I mentioned that JavaScript is special. Don't get me wrong, I love these languages. Part of the reason I make fun of these languages is because I love them. And in fact, JavaScript is so beautiful. I wrote, my most recent book was on JavaScript, and I love this language. But of course, JavaScript is also very special. And I was programming with JavaScript one night, and of course, like everything else, things did not work. And when things didn't work, you're struggling to find out why it is not working. And in the frustration of debugging my code, I tweeted something, and I believe truly in what I tweeted. And here's my tweet. Here's how I describe JavaScript to other people. JavaScript is like an infant. It is cute to play with, but you have no clue why when it begins to cry. So this is like the baby is crying. You call mom and say, Mom, the baby is crying. I don't know why. And mom says, have you checked the diaper? I did. Have you fed the baby? I did. Is there a little insect nearby? Nothing. And you're debugging the baby, right? And that's what you're doing, trying to find out why the baby is crying. That's how I feel about JavaScript code sometimes. You don't have a clue why it's not working when it doesn't. But of course, it's extremely powerful language. But if you really think about it, the world is ruled by weakly typed languages. Our servers run on languages built around C and C++. Our client side run on JavaScript. It's kind of scary that the whole world is actually hinging on weakly typed languages. But having said that, though, when it comes to programming language paradigms, what is really intriguing to me is it's easy to learn a syntax. It's easy to learn a library. It's easy to learn an API. But what is really hard in terms of a programmer's effort is learning a new paradigm. And I've been programming for a long time, and I'm going to say I probably have learned about 5, if not 6 programming paradigms in my life. And I remember every one of them was incredibly difficult. The very first programming paradigm was programming itself. And that was really hard for me to learn that you can actually program a machine to do something. It took me a while to figure this out. So the first step was to start to program. And I started programming in procedural code. Back in time, I used to program in languages like BASIC and Fortran and Pascal and C. That's what I did in the beginning part of my career. Then I started learning about structured programming, and then eventually I started learning about object-oriented programming. And that was a journey to learn about objects, to think object-oriented, to learn about polymorphism. That was a lot of effort to go through that journey. And once I think I figured out how object-oriented programming works, my next journey was to learn about distributed computing. Some of you may be old enough to remember the dark days of COM and CORBA. I would never wish that on an enemy today. But I remember waking up in the morning with the fog around my head and saying, I don't have a clue how this works. And I'm not a person who is happy when my code works. I'm actually very unhappy when my code works because I want to know why it works and how it works. And I want to break it and put it back together. And I remember spending months trying to understand how COM and CORBA worked. And if anybody ever told me the word object factor, I'll strangle them one more time because it's annoying to be dealing with these object factories. But once I figured out how this works, that was like, wow, that's amazing. How these communication works across these remote calls and COM and CORBA was a really hard journey for me. Then I wanted to really learn about functional programming. And what really made worse about functional programming is everybody who was good at functional programming told me it's easy. I'm like, no, it's not. It's really hard to think functionally because I'm used to thinking imperatively with mutability and state change. And now I have to think about a problem as a state transformation. And that was a really hard journey for me to learn about functional style of programming. And then when I thought I was done, then they were talking about reactive programming. And here we go again. What in the world is reactive programming, and why do I care about it? And that was a journey again. And almost every literature I read only made me angrier because they all were talking about how you could do wonderful things. I'm like, show me the code kind of a person. And it took me a while to realize that reactive programming is actually functional programming plus. It's built on top of function composition and lazy evaluation. And then, of course, you are dealing with the streams of data. So going through this journey of paradigm shift was really interesting journey to understand and adapt these different paradigms. But when it comes to these paradigms of procedural, structural, object-oriented, and functional, every one of them have certain capabilities. In procedural, of course, we write procedures or functions. Structured programming, of course, gave us a set of discipline. It said there's got to be a really clear structure, and the if and else conditions, and an entry point and an exit point. Of course, the good old famous article by Dijkstra, where he said that goto is evil, and we should not program with gotos. Now, of course, object-oriented programming gave us this ability to think about objects as encapsulated boundaries, capturing behavior, not as much state, even though we kind of went in that wrong direction. And functional programming is really an encapsulation of functions as these transformation engines, and we have composition of functions and lazy evaluation. But then I started thinking, if these are different languages, are they so widely different? Or are there anything common between any of these languages? And I'm going to say there is something that intrigues me a lot, and there is not a day in my life as a programmer I don't pause to thank one person. And I'm sure that's true for you as well, because it's so fundamental. If anyone wants to give an award for somebody in our field, that award should go to this one person, in my opinion. His name is David Wheeler. And David Wheeler said something absolutely phenomenal. And David Wheeler said that in computer science, all problems can be solved by introducing another level of indirection. And to me, this is the most profound statement in our field, hands down. And the reason I say this is, we do this every single day. And we do this so naturally sometimes we don't think about it. But honestly, when I'm struggling with the problem, I often pause to think about David Wheeler's comment, and that makes it easier for me and gives me hope for me to solve a problem. Because I can solve a problem by solving a small another problem, which I can direct to this other problem, a level of indirection. And then I ask the question, if this is so fundamental to what we do, then it doesn't matter what programming paradigm we use, there's got to be a level of indirection in it. And that's why I think the level of indirection is the common thread between paradigms. And every single paradigm offers a level of indirection. And this is one of the luxuries I have, is the ability to sit back and think about it and not have to really write any production code on a day. And I can just think about this and say, what would be a level of indirection? And I answer this question by thinking about procedural programming. In procedural programming, there's a level of indirection. And what is that? And we know that the level of indirection in procedural programming is pointers. And pointers give us the ability to point to a function or an object or a structure, and then be able to switch to another function or an object or a structure. And this is extremely powerful. And it is so powerful that this permeates almost every single modern language. You may be wondering, what about Java though? In Java, we don't use pointers. And that's what I want to say. The people who wrote Java, who designed Java, are brilliant. Because when Java was being introduced, the most popular language was C++. And you don't go to C++ programmers and you never ask the question, how do you feel? Because they don't feel too well. Because they've been burned by pointers. If you're not trusting me, find any of those C++ programmers in the room and go close to them, you will see scars on their body. If you ever come close to me, you'll notice I have scars actually on my face. That was from one of the pointers that caused it. And essentially, C++ programmers hated pointers because they had to deal with every day. So when they introduced Java, people were immediately curious, and they asked, are there pointers? And they thought about it and said, of course we cannot say yes, because nobody would want to adapt Java. So they were very clever. They said, no, we don't have pointers, we have references. What are references? Pointers. We just don't call it pointers, then people are very happy with it. Well, Java is full of pointers, but we call them references. What Java removed was not pointers. What Java removed was pointer arithmetic. And as a result, it removes some complexity, but we cannot live without pointers, and that's so pervasive. That's a level of indirection, and we see this in Java as references as well. Well, that brings the question then, if that is true, object-oriented programming should have a level of indirection as well. And it turns out it actually does. Because if you look at object-oriented programming, the level of indirection in object-oriented programming is polymorphism. Because polymorphism says the method that is executed at runtime is not based on the type of the reference, but it's based on the type of the object at runtime. And that gives you the level of indirection. You can write the code with a reference, but you can indirect it to a completely different instance at runtime thanks to polymorphism. And then that brings the question, if level of indirection is so important, how in the world could we program in functional style without having a level of indirection? And so that got me thinking, what is the level of indirection in functional programming? Well, think about it this way. Suppose I have an apple, not a computer, but a fruit. And if I give you an apple, there are 4 things you can do with an apple. A, you could eat it right away. Maybe you're hungry. And the minute I give you an apple, you just eat the apple. So you could be eating the apple. Or you could save it for later and say, I'll eat this during lunch or during a break. Or you might give it to somebody else. You may give it to the person next to you and say, hey, I got this apple from Venkat, but you can have it. Or you can throw it away into the trash can. So if I give you an apple, you can eat it now, you can eat it later, you can give it to somebody, or you can throw it away. Well, imagine in a similar way, I don't give you an apple, but I give you a lambda. Well, a lambda turns out to be a level of indirection because when I give you a lambda, you can execute the lambda right away, or you can pass the lambda to another function. You can save it to execute later on, what we call as lazy evaluation, or you may throw it away, in which case you don't execute it at all. You defer it so long that you don't care to execute it ever. So it turns out these levels of indirection are so pervasive that we cannot imagine programming in a paradigm without having a level of indirection, and almost every single paradigm has a level of indirection we can benefit from. So one of the problems, though, is when it comes to these paradigms, I call this the misguided conversation. And I'm a bit frustrated when I hear people often compare between object-oriented programming and functional programming. I've got good friends, honestly, who do this. And we are still good friends. We simply agree not to talk about this when we get together for dinner. And the point really is, I truly believe this is a misguided conversation because your enemy is not object-oriented programming. Now, sure, I get this. A lot of people complain that OOP has been done very poorly. Well, sure, but a lot of things have been done poorly, but our enemy is not object-oriented programming. The real conversation is not the difference between object-oriented and functional. The difference is imperative versus a declarative style of programming. Well, we have been, as a mainstream, we've been programming an imperative style for a very long time. And of course, the world is moving towards more of a declarative style of programming. So the real question is, should we program imperatively or should we program declaratively? And which one should we really choose? And that's what we are really going towards. What is the difference, though, between these things? Well, imperative style of programming is where you tell what to do, but you also have to spend the time and effort telling how to do it. So not just the what, but also the how. Let's look at an example just to get a feel for it. So here I have a little program. I have a list of names, but I want to know if our good friend Nemo is in the list. So how do I find if Nemo is in this list? What's the very first step I'm going to do? Well, the very first thing is I'm going to define a Boolean found is equal to false. That's the very first step, isn't it? And of course, if found, what do I want to do? I want to output Nemo found, and we can celebrate that. Otherwise, what do I want to do? I'm going to say Nemo not found, and maybe we'll play a sad music. But how do you change the value of found? How do you go about doing it? Well, for that, I'm going to say for, and I'll say string name. This comes from the names, of course. And then what do? I say if name, and of course, you don't put equals, because you need to put dot equals. Well, you have to make all those decisions at this point. If it equals Nemo, what do? Then you say found is equal to true. As an observant reader, you'd say, oh, Venkat, you're not done. You better put a break statement right here. Otherwise, the program may be incorrect or at least poor in performance, depending on the situation. I know what you're thinking. You're looking at this code and thinking, gosh, I never would write code like this. You would normally say F or T or temp, because that is how you tell the variable how you feel about it. You don't deserve to live. We don't like these kinds of variables, isn't it? Well, those variables are called garbage variables. They're not needed to solve the problem. They're needed only by the solution we chose to use in this particular case. When I run the code, it says Nemo found. That is an example of an imperative style of code, as we can see. So how does it? So I'm not going to ask you the question if anyone here has written imperative style code, because I know every single one of you have done that. But I'll ask you a different question. How do you feel when you write imperative code for 8 to 10 hours a day? I'll tell you how you feel. You feel absolutely dirty. And you feel dirty having written this code for 10 hours a day. You go home, and the kids come running towards you. You say, don't touch me. I got to go shower first. That's how you feel about it, isn't it? And you kind of smell, and you say, what's all that smell around you? And that's what happens when you code imperative for 8 hours a day. When you code imperative style, how does it feel? It feels like you're talking to a toddler. Well, the day you first talk to a toddler, you're like, wow, this is amazing. I spoke to this little baby, little kid. And then what happens the next day? You realize it's the same old thing. You got to say the same thing to the kid. Walk slowly, hold it with both hands, and please don't step on that cat again. And then you realize this is going to continue for the next 18 years. That's called parenting, isn't it? That's how you feel about it when you write code like this. So what can we do differently about it? Well, this is where the declarative style of programming comes in. You tell what and not how. So how would this code look like if we decide to program in the imperative style? Well, here's the beauty. Without having to write all that code, let's remove all of that. Let's only focus on the last part right in here. And let's take this if, but rather than using the variable found, what if we said names.contains Nemo, and then we can, of course, execute the code right off the bat, and it tells us Nemo found and produces the result for us. Now look at this code, contains. That is an example of a declarative style of programming. So declarative style is where we tell what to do and not how to do it. But of course, a reasonable question to ask is, can anyone guess how contains actually works? Any ideas? Yeah, that's the first answer. You could simply say, hey, it does what you see up there. That's one answer. I like it. Is there another answer? Yeah, maybe you could say, oh, maybe it's very efficient. Maybe it's using a very fast algorithm. Maybe it gives you a better performance. Well, that's a great idea too. It's the third answer. I like that answer. It's called, I don't care. Okay, that sounds really rude. Why would you want to say, I don't care? Let's say it in a polite way. It's encapsulated. What does that mean? I don't care. That's a much polished way of saying it, isn't it? So I don't care. It's encapsulated. But of course, you and I know something really well as programmers. We do care. Because we look at a piece of code and say, huh? What does it do? Does it pollute a memory? Does it have a good performance? But there's a big difference between the code in the top and the code in the bottom. The code in the top gives you no choice. It has all the details on your face. It never gives you an option. The code at the top is like that old uncle who is annoying. And when you see this person, you take the other elevator. Because the minute you saw this person, you're going to hear them speak for an hour like I'm speaking right now. And the point is you're like, never mind, I don't want to hear this. Well, you don't have a choice in the code on the top. But the code on the bottom, that detail is one click away. You can gently click on it and say, show me the implementation, and you can take a look at it. It's not on your face, but it's within your reach. And you can look at it when you want to and not be bothered by it if you don't care about it. But that brings the question, if that's what imperative and that's what declarative is, where in the world is functional programming sitting here? Well, functional programming is declarative plus the use of higher order functions. So you're mixing these two ideas, and one of the reasons I'm excited about functional programming is declarative in nature. And because it's declarative in nature, it gives me the power of expressiveness, and as a result, I can build on that power very easily. But of course, imperative style is where we focus on what to do and how to do. Imperative style code is easy to write, but it's hard to read. It is easy to write only because we've been doing this for a long time. I've been programming in imperative style for a good 35 years. I spent my childhood writing code in imperative style. What I'm telling you is I had a very terrible childhood. And I had to spend all this time writing imperative style code and debug it. And of course, it's hard to read because you look at the code, and here's a phrase you will hear people often say, let me figure out what the code is doing. That's a sign they don't have a clue what the code is doing. They got to dig into it. Functional style code, on the other hand, is declarative. You say what to do, not how to do it. And I'm going to say functional style code is easy to read, but it's hard to write. It's hard to write mainly because we just don't have the experience writing the code in it. I've been programming in functional style maybe only for about 10 to 15 years compared to 20 more years programming in imperative style. And I was on a flight recently. And honestly, I'll be honest about it. If you give me a problem, I can write the code in functional style maybe 50% of the time. The other 50% of the time, I still have to struggle to think about it. It's not natural for me yet. And people will tell me, oh, it's easy, but honestly, it's not for me. And I'm struggling with it sometimes. And I remember taking a flight from Europe to the US, and when I got on the flight, immediately I opened my laptop, and I took a problem, and I wanted to solve it in functional style. I wrote the imperative code in 10 minutes, and I spent 8 hours on this flight trying to write this code in functional style. Trust me, an exercise like that beats any in-flight entertainment. Forget about watching a horror movie in the flight. This compensates for it. And every few minutes, the flight attendant will come and say, are you okay? I'm like, yes, I'm fine, just trying to figure this code out. That's all it is. And you're trying to really understand this. And then a bulb goes in my head. I'm like, whoa, wait a minute. And it works. And then I'm like, gosh, why did it take me 8 hours to figure this out? Well, that's because there's a mental block usually, and you're trying to think, and you're trying to force your mind to think functionally when it's used to thinking imperatively. But if you give me a functional style code, it is so much easier to read it. The code begins to flow like the problem statement. I can step through it and understand what the code is trying to do. But of course, one problem is imperative style code becomes progressively difficult and harder to work with. Let's look at an example for a minute. We can say simple problems should be easier to solve, and more complex problems should be manageable. Let's take a simple problem here. Print, comma, let's say, separated. And what do I want to do? I want to say print, comma, separated, names of length, let's say 4 in uppercase. That's a very simple problem, isn't it? I want to print the names, comma separated, in uppercase of length 4. Well, let's do it. So for string name coming from names, how hard could this be? Output the name. Well, that's printing all the names. But I only want names of length 4. So name.length, of course, is equal to 4. And I'm going to then print only the names of length 4. But of course, it wants us to print them in uppercase to uppercase. And we can print that in uppercase. But of course, the problem says print it comma separated, so we can print it comma separated. But what they really meant was on a single line, and I'm going to print it all on a single line. But when I do this, oh my gosh, look at that. There's a stupid comma in the end. Has anyone seen this problem before? Yeah. How did you feel when that happened to you? You were in denial, isn't it? You looked at this and said, this cannot be true. How do we remove that comma from the end? And you're thinking about it, and then you realize, oh, damn it, the string is immutable. And then you're thinking about it a little bit more. And then suddenly you come up with this brilliant idea. You say, hey, I got an idea. We'll put it in a string builder and strip it. And the minute you say it, your colleague is a string builder or a string buffer? And you have a 20-minute discussion about it. And then you're struggling with it, and then somebody says, come on, this is a simple problem, there's a simple solution. You're like, really, what is it? Oh, very simple. Just don't print the comma if it's the last element. Why didn't I think of it? If it's the last element, don't print the comma. How do you know it's the last element? Oh, that's very easy. All you have to do here is simply say int I equal to 0. How does that feel? 30 minutes later, you're still working on it. In the meantime, the boss is like, are you done yet? How come this becomes so complex when the problem is so simple? Let's try this again. Let's go ahead and say output, and we will say names.stream.filter, and I'm going to say given a name, name.length is equal to 4. And then a map of string, and I'm going to simply say to uppercase, so we'll convert it to an uppercase. And then, of course, we'll say collect. And in this case, we'll simply say joining. And we'll join with the comma. And that comes from the collectors API. So it turns out the code is actually extremely simple to write once we think about it in a functional style. So we can say, given a collection of names, give me all the names which are of length 4, convert them or transform them to uppercase, and collect them comma separated. And of course, it gives you a string object, and you can print it. So that becomes a lot easier to work with. And as a result, the functional style becomes progressively easy. Imperative style becomes progressively difficult. So with that said, clearly, functional style is better, right? So we should be programming in functional style and quit using imperative style, isn't it? Well, I've been wrong, and I've been wrong many, many times, and I'm sure I'll be wrong again. But one of the things to really think about is, how can we do what we do better? And to me, one of the things is continuously learning. I'm not suggesting we should be whimsical, we should just change our mind too often, but we should be willing to change our mind as well. As much as it is, I used to program in imperative style all the time. I used to program in functional style mostly then, and then I realized maybe that's not really the right answer to say one clearly is better than the other. And it's a balancing act. We have to know which one is better and when, and we have to make the choice we do. So to answer that question, should we program in imperative style or should we program in functional style? And to answer that question, I want to look at something completely different. I know this is more exciting than what we do, but nevertheless, it's pretty exciting to think about. Let's think about light. And this conversation happened a good 100+ years ago between people like Einstein and Planck and so on. And there was a time when humans were trying to understand the nature of light. And it turns out light exhibits the properties of a particle. And so the humans decided to say light is a particle. And then they realized that there were experiments they were conducting, and while light behaves like a particle, there were results that showed that it exhibits nature that is not like a particle as well. For example, refraction. Why do I see multiple shadows at any given time than just seeing one shadow depending on where I stand? And that didn't really explain the particle nature. And we know what this is today. This is called is light a particle or a wave? And that's the wave-particle duality. I know that's really exciting, but light exhibits both the dualities of being a particle and a wave at the same time. So a light is not a particle, light is not a wave, it's actually both. Well, I'm going to say we have somewhat of a similar of a dichotomy in our field, and to me that is the imperative functional duality. So in programming, my question is, should programs be imperative or should programs be functional? And I'm going to say the answer to me is that it's neither one of them. And there are times when the code has to be imperative, and there are times when the code has to be functional. And I think it is very naive to say it's got to be entirely one and not the other, whichever you may choose. And there are times when imperative makes really good sense, and there are times when functional makes really good sense, and there are times when you need to really choose between one or the other and not be adamant about it. So imperative is really good when you have to deal with side effects and when you have to deal with exceptions. So typically, you would have to write code where you do have side effects. That is something you cannot get rid of entirely. And especially with legacy applications we work with, and the traditional applications we develop, and applications that require a lot of good performance, we absolutely may have to go to side effects. And of course, exceptions are the nature of what we deal with oftentimes. Things do blow up, and especially when you perform I/O operations or call into remote services, exceptions are the way of life. How do you write code in functional style to deal with side effects and to deal with exceptions? And the short answer is not very elegantly. And when people try to do these things, if you go the route of what Scala does or the route of what Haskell does, I would argue while you may implement a solution, the code is not very cohesive. It becomes really hard to conceptualize the idea and implement in a meaningful way, and it becomes complex. What is simple and elegant is no longer the case, and it becomes really complex over time when you have to deal with these issues. On the other hand, functional style code is really good in dealing with scale and parallelism and reasoning. So in that regard, there are times when one is better than the other. And the capability of modern languages to me is beautiful in that most of the languages, thankfully, give us both of those. Look at languages like Java and C# and Python and Smalltalk and Ruby and Groovy and Kotlin and Scala and keep going. A lot of these languages give you multiple paradigms in it. We can shy away from those languages, but there is merit to really asking, hey, the fact that they give me both, it treats me as an adult to say, I will give you the option to pick and choose what you want to do, and you are free to choose on a given program which way you want to go, and even within a program, you can choose. So one of the nice things I like about the functional style of programming is the structure of sequential functional code can be the same as the structure of concurrent functional code. Now think about this for a minute. If you wrote an imperative style code with all that for loop and while loops and all that and if statements, and when you wrote the code, maybe you wrote the code as a single-threaded application. How do you know you're writing a single-threaded code? I'll tell you how you know. You go to work and everybody smiles at each other. That's a sign that you're writing single-threaded application. And the team goes to lunch with each other and you're friends with your colleagues. That's a single-threaded application. And then after about 6 to 7 months, somebody says, the code doesn't perform really well. We got to improve the performance. And you all talk about how to do it. And somebody has a bright idea. They say, why don't we use threads? And what happens when you start using threads? 3 things happen. The first is your beautiful code turns into a monster. You don't recognize it anymore. Second thing, nobody smiles at each other. You come to work, you're grim. You sit there and code. Everybody is angry with each other. And don't even talk about going to lunch. You got bugs to fix now. And that's when a sign of functional style, imperative style code that becomes a monster. So what do? You're struggling with this code, and late in the night, you're debugging this, and you've had enough. And you decide, that's it. This is not for me anymore. This is ridiculous. This application can never work properly. And what do? In the middle of the debugging, you applied for this other job. That's called concurrency, isn't it? And you're like, I'm done, I'm checking out. Well, the good news is, Java 8 Streams gave you this capability nicely. When you run the code, you have the code working, but you can simply come here and say parallel stream. If the collection were really large, all you have to do is make it a parallel stream, and you get exactly the same result, but you can quietly make it parallel versus sequential. You can change it very easily at will. So all that you had to do was simply make a small change to the code. I call this a master switch. The structure of the code is exactly the same. All you had to do was decide to flip a switch and make it concurrent versus sequential where it makes sense. So to me, one of the nice capabilities is the sequential code and the concurrent code have the same structure in the functional style thanks to streams. But what about exceptions? What about handling exceptions and failures and side effects? Well, functional style code is not elegant to do it. This is one of the reasons why I am interested in thinking about alternatives. Let's look at an example really quickly here. This is an example from JavaScript. I know that's scary, but I think we can learn from everything. So this JavaScript example, I have a function called compute. And a compute is a sequential code, a synchronous code. Don't worry about what compute does at this point. But I want to make a call to compute. So I have a function called call I'm going to make. And within this call function, I'm going to put a try and a catch because there could be an exception. I put a try and catch. That's imperative nature. I call the compute function, pass a 2 to it. I get a result back. Then I print a message saying, I've made the request. If the call to compute is synchronous, you know you will not print made the request until the call is completed. And then I print the result of that call. And if there was an exception, I print it. And then I finally make the call, and I move on. So this is pretty much a sequential code, a synchronous code. So the compute was called, you made the request, and you print the result, and you're done. But look at the structure of this code. But I want to make this code asynchronous. And I'm going to say, moving forward, this is one of the things we're going to do more and more. As much as parallelism is really exciting, asynchronous programming is where we're going to invest more and more in the future. And asynchrony is going to be the way of life thanks to big data and microservices and web services and the service-oriented systems we are building today. So as a result, how does this code become if I want to do asynchronous coding? Let me just copy that code in here. Right now, as you can see, these two are the same piece of code. I'm flipping between the two versions right here. But I want to make it asynchronous. So what am I going to do to make it asynchronous? In the synchronous version, make the request came later. I go to the asynchronous version, and I mark this function as async. That's what I just did. And the minute I mark it async, I can call the asynchronous version, which is returning a promise in the case of JavaScript. And once it returns a promise, I can await on the promise, and then I can respond the result when the result arrives back. Now you can see the code is non-blocking. And it said made the request first, and then it made the call to the asynchronous function. So it is non-blocking, but notice the code structure is exactly the same. And I don't have to deal with a completely different structure of the code. What's the benefit? Easy to understand, easy to design, easy to debug, easy to work with. And when I need the performance, I can switch over to asynchrony. So if we can do this, this becomes really easy for us to work with. Now, this opens up door for some incredible things we can actually do. Like what? Let's think about this for a minute. How we can keep the structure of the code the same, but we can exploit concurrency and asynchrony quite effectively. So from that point of view, let's create an example code in Kotlin here. I'll call it as task 1 for a minute. And task 1 simply takes, let's say it doesn't take anything, but in the task 1, I'm going to simply print out entering, let's say, a task 1. That's what I'm going to call right here. Then I'm going to go ahead and print out, let's call it as exiting, let's say exiting task 1. I'm going to create one more. We'll call it task 2 over here. And this is entering task 2 and exiting task 2. But before we go further, I'm going to add one more. I'll simply say let's say thread.current thread. So we can print out the thread details here as well, so we can see which thread is executing this code. So we are entering the 2 tasks here, as you can see. Well, then what I'm going to do here is bring in, let's say, import Kotlin x.coroutines.star. And at this point, I'm going to bring in a run blocking. So I'll just wait for this coroutine to complete. I'm going to call task 1. I'm going to call task 2. But I'm going to then report a called them. And then I will just go ahead and print out thread.current thread right in here. This is a very simple sequential code at this point. That's all I have so far. Nothing really exciting. So when I go back and run this code, what is going to be the output of this code? Well, when I run the code, you can see from the output, you entered task 1, and you finished it fully, and you exited task 1. Then you entered task 2, and then you exited task 2, and then you said call them, but all from the main thread. But what if I want to make it asynchronous? What if I want to make it parallel? How do I go about doing it? Well, before we talk about it, I want to spend a minute talking about 2 different things, a parallel versus concurrent. Now, this is a source of confusion to a lot of people, including me. What is concurrent? What is parallel? How does it really matter? Well, in this case, I want to make them concurrent. And so what does that really mean? So to understand this, let's take a little exercise and play with it for a minute. I want one volunteer who wants to join me here to help me out with this. One person. Don't be shy. Who wants to come? Yes, please, come on over. What's your name, sir?
You can call me Sam.
Sam is good. Cecile is good. So let's do an exercise here. Let's come over here for a second. So we're going to demonstrate parallel versus concurrent.
Okay.
Are you ready?
Sure.
All right, let's just walk over here. So this is parallel. You're walking, I'm walking.
And now we're trying to be concurrent.
Now we're, well, no. Don't go faster. I'm an old man. Don't go faster.
Okay, sorry.
How are you doing?
Fine.
You have a good day?
It's a good presentation, yeah.
I'm not talking about the presentation. Is it having a good day?
The day is good.
The weather is awesome?
Not here.
Not here. Well, look at this. It's beautiful sunny, is it?
It's true.
Yeah. So we just demonstrated parallel and concurrent. How so? We are walking in parallel. We are talking concurrently. We are civil people.
Oh.
Yeah. We are civil people, isn't it? You're not talking over me. I'm not talking over you. I say something. You say something. I say something. So we are walking in parallel. We're talking concurrently. Does it make sense? So that's basically, and thank you for the help. So let's give him a hand for being so courageous to walk up here. So that's an example of concurrent versus parallel. So parallel is two things progress exactly at the same time. Concurrent is also progressing, but it's like a conversation. You say something, the other person says something, so we go back and forth, and that is concurrency. So as far as you are concerned, you are hearing either me or you're hearing him. You're not hearing both of us at the same time. Because if you hear both of us at the same time, that's going to cause race condition in your head. That's going to be really hard for you to deal with. So the point is, we can walk in parallel, but we talk concurrently. Let's see how we can bring concurrency to this code. I want you to think about this for a minute. The code is executing in the main thread, all of them in the main thread. But I'm going to come in here, and I'm going to then say over here, a launch. So I call launch over here, and I'm asking it to delegate these two to run in a completely asynchronous manner. But when I run this code, though, I didn't specify the thread of execution, so the main thread actually runs them all. So as a result, the thread is still main, as you can see in here. However, it says called them came first now. As you can see, a minute ago when I didn't have the launch, when I run the code, called them is coming at the very bottom, as you can see, because it made the calls and blocking. So at the moment, every one of those calls is a blocking call, and we see call them in the end. On the other hand, I put the launch right in here, and now that I call the launch when I execute the code, you can see in this case, it is non-blocking. So it didn't call the task 1, didn't call task 2. It executed the last line, then it executed task 1 fully, then it executed task 2 after that. On the other hand, I can make this completely non-blocking, and I can use a keyword here to do this. I can say suspend over here to say that this particular function is suspendable. And now when I execute the code this time around, you can see it's still in the main thread. However, we called them first. We entered task 1, but we entered task 2 as well at that point. Well, I didn't put a yield, didn't I? So let's do that. I say yield over here. And then, of course, I'm going to come in and yield here as well. And in this case, when I run the code this time, you can see how we call the functions, but we entered task 1 and we entered task 2 as well. But notice we're still in the main thread. And then we are exiting task 1 and exiting task 2. So this gives an ability for us to become non-blocking. And so when you are making a call to a service, you can simply say, hey, let's not block my main thread waiting on it. Let that go off and do things asynchronously. I can proceed to do my work. And this becomes concurrent. So this code is concurrently running task 1 and task 2, just like how he and I were concurrently talking to each other. So this gives you the flexibility to keep the code structure the same. If you notice, the structure of the code did not change, but we are able to go from sequential to asynchronous and concurrent without changing the code structure, and there is good merit to it as well. So given this, languages should really enable and not limit our form of expression. And I care a lot about the forms of expression. And there are times when imperative style code makes sense to me. There are times when functional style code makes sense to me. And I want the flexibility to choose wisely when I want to. So I want languages that give me the capability, and thankfully there's a lot of languages that do give us that capability. Kotlin, Scala, Java, Groovy, Python, Ruby, Scala, name a few for example. So the point really is a lot of languages, including JavaScript, not to exclude it, gives us this capability to do the mixed paradigm. And I think there is merit to it, and there is nothing wrong in choosing the paradigm that actually makes sense to what we want to do, rather than really saying that's the only way to do it. So in that regard, what if I view languages like a hybrid plane? There are times I want to be in the sky, but there are times I want to land, not just on the land, but on water as well. And what if I think about languages and the paradigm not as a switch, but more like a thermostat? Maybe that the weather is really warm and I want to make it a little more comfortable in the room. Or maybe the weather is really cold. I want to make it a little bit more comfortable, making it warmer. Or maybe I want to leave it right in the middle. Maybe there are times I want to be imperative, and maybe there are times when I want it to be more functional, or maybe I want to just balance it out. And I want to be able to set that thermostat based on what I am trying to do. And I'm going to say that progress is impossible without change. And those who cannot change their minds cannot change anything. And that is one thing I want to challenge is, it's okay to have convictions. It's okay to have our preferences. But it's also important to be willing to change. And if we are not, after all, willing to change, then we are not going to be able to afford any change ever in the future. So in that regard, when it comes to programming paradigms at least, and for a lot of other things in life, I would say that it is not one way that works all the time. And I'm going to conclude by simply saying, wisdom is realizing that there are no absolutes. And to realize that there are different options, and we need to be willing to choose between the options and come back and learn new things as well. And so I'll conclude by simply saying, wisdom is realizing that there are no absolutes. Hope that was useful. Thank you.
Thanks, Venkat. So we have about 10 minutes for asking the questions. Just raise your hand. I'll bring a microphone. You'll ask questions in the microphone so we can record this.
Hi again, Venkat. So you've been showing code snippet with the problem of adding comma at the very end of the statement. But the solution that you've shown is far more advanced for beginners at most, and it's far more hard to understand. So in your opinion, maybe it is a good idea just to leave the comma out of scope, like don't print it.
So one of the things let me take your question and take it a little bit more fundamental, because your question is very important. Our industry has people with enormous differences in experience and maturity as well. Somebody may be really a beginner, but they may be really capable and advanced because they've invested time in learning, versus somebody may have worked for a few years, may not be really as mature or advanced. But nevertheless, one of the things we should really focus on is, I'm not a big fan of this idea of dumbing down things because somebody else may not be able to deal with it. I would rather provide the correct solution and a preferable solution, but raise the bar of the team. And in that regard, I think one of the things we are doing really bad in our industry is we are expecting people to work in isolation. And the more I spend time, I realize that my strength is not in being isolated. My strength is learning from other people who are smarter than me. So what if we take these beginners that you mentioned, and we tell these beginners, you're not required to work alone. This is not a competition. You're not going to be left in a room and put to a threat saying, if you don't deliver this code, you're fired. Instead, we tell these beginners, you have no real responsibilities other than working with somebody of experience, work with them shoulder to shoulder, program with them, and imagine how quickly this beginner becomes a more advanced programmer. So I think we should really solve the problem not by dumbing down the code, but by elevating the team members, by giving them the capability to acquire that skill and knowledge much more rapidly, I think.
Okay, thank you.
Sure.
Okay, any other questions?
My name is Sergey. So you saw us different paradigms that we can use in Java, but how about readability and maintainability? When we saw methods in the same class written in different paradigms, it can be frustrating, and as you mentioned, different guys has different experience in imperative or functional programming, and it can be a lot of holy wars on code review, how to implement something. So what is your opinion?
Fair enough. And I think there are at least 2 or 3 questions in your questions, so I'll kind of split them and answer them separately. The first is, what if we open a piece of code and we see multiple paradigms in it? Can it not become really frustrating? So one of the things I will emphasize is programmers are extremely skillful to write bad code. So it doesn't matter what paradigm you give them, they can write bad code. If you don't believe it, I'll show you some of my code, and you will know how bad it can be. But the point really is, in every paradigm, we can write code that is easier to understand and easier to maintain. And a few rules I'll follow for that. One is really good variable names, really good function names. Make the code cohesive. It doesn't matter whether your code is functional or imperative. If you give me 3,000 lines of code in a function, that's morally wrong. It doesn't matter what the paradigm really is, isn't it? So if you write code in imperative and functional, but if you followed good coding practices, keeping good variable names, both in functional and imperative, keeping the methods, functions small, and making them cohesive, then it's really not that difficult to understand. And the chances are that somebody who understands functional also understands imperative, and vice versa as time goes on. So if the code is of good quality, it's easier to maintain, understand no matter which paradigm that is. If the code becomes absolute rot, then absolutely true, but the problem there is we let the code run afoul rather than making a good quality code. The second part of your question was about the wars that we enter into during code review. Now, this is one of the things to keep in mind is that our efforts to what we solve is technical, but only partly. It is also a people problem. If you and I have absolutely the greatest attitude with each other, if you and I are really good friends, we are going to listen to each other and help each other out. If you and I don't like each other, it doesn't matter what else you give me, I'm going to find a reason to fight with you. So even if the code is in one paradigm, it's going to become really a negative experience. So I would actually address that as a separate one. And in that regard, I never encourage teams to have a massive code review. Code reviews are a bad idea when it is done that way. What I like really is a very tactical code review where you write code and one other person reviews the code, not a team putting the code on the screen. And when that person reviews the code, we follow a certain practices. A code review is an encouragement for you to improve the code, but it's also an opportunity for me to learn from that code as well. It's not always a way to say, I'm going to be scrutinizing your code. That's not the way that I look at code review as. A code review to me is a chance for you to improve the code when I review it, and a chance for me to learn from that code as well. And the suggestions I make are simply that. They are recommendations. I'm not going to come home with you and sit and say, I gave you a code review today. I'm going to wait until you finish it. Well, it's a recommendation. We need to treat each other with respect as professionals and say, this is my opinion, take it or leave it, depending on your judgment. So when the attitude is really good, then it becomes a much pleasant place to learn and work with each other. So I would address that problem, then try to remove the technology because we got poor attitude among people to work with.
Thank you. We're running out of time. Now it's time for a coffee break. If you have any question, just feel free to reach Venkat during the coffee break. Thank you. See you in the next talk.
Thank you.